Right. So let's look into the theoretical results associated with duality that guarantees us that we can use duality as a framework to find solutions for our primal problems. So there are basically two main results. The first one is what is called weak duality. And a weak duality is the one that states that duals can be used as a bound for your primal problems. So let us define our primal problem like such, coming back again to the canonical form to make things a bit easier notation wise. And then we have our dual written as our like such, which is the dual we will obtain for that primal in that canonical form. And the weak duality basically is this: the very first result we kind of discussed. You're using the dual as a lower bound for your primal minimization primal problem. Okay. And to see that is actually sort of straightforward. So let us define these two sets of constraints and variables, ij, like we've been using before. And for any x and for any p, that is, feasible to the original problems, we like it said here, we have the following. So this ui term, which is basically the product between pi and the difference between aix and b for each row. So this is the penalty term that we were talking about in the previous video. And thinking of v, which being a similar thing, but now looking at what would be the equivalent when you dualize, when you relax the constraint associated to the other in the dual. So basically, because we're talking about feasible p's and feasible x's, what we're gonna get here is that ax is greater than b, so this is positive, and c is greater than pa, so this is positive, although negative in both cases. So, and because we have constraints of this being greater than equal than 0, this term is clearly greater than equal than 0. And in this case, remember that this is going to the objective function, so you don't want to make this negative, so you will be stimulating infeasibility. So it turns out that this thing is also assumed to be non-negative, such that this thing is actually working as it's supposed and being minimized. So this u and this v is not easy to convince. It's not hard to convince yourself that they actually non-negative because of what we're just talking about. And that will kind of lead us to the following. So when we look at the sum of all the u's and the sum of all the v's, this is greater than equal than 0, as we just seen. And then basically I'm opening up u by pre-multiplying both terms in the parentheses. I get something like that in the matrix form. And doing the same here, I get cx and pa x. And then I can see that this term cancel out with this. So basically what this is telling me that this minus this is greater than equal than 0, which is the same as saying this. And that proves that duals are indeed lower bound for the primal problems. And that's the weak duality result. So this is one of the key results in duality that we use, because it means that duality can be used as a framework for giving upper bounds to your current solution. So one interesting application of duality we'll see later on is that, once again, suppose this is the axis of my z values and I'm searching for the z star. Because I'm minimizing, whenever I find a primal feasible x that is not necessarily the optimal, I might be at some point saying here, for a given x, I know I found an intermediate vertex in my simplex method, for example. And also, so this is going down as I progress in my algorithm, solving my original problem P. And when I'm solving my dual, what I get is a lower bound, which is just what we just proved. And when I'm solving my dual problem, I'm maximizing in terms of P, I'm moving these upwards. So this difference here, it's something that is called duality gap. And it can be used to tell you how far away you are from your optimal. You're not further than the relative difference between these two. You know that your optimal has to be in between these two values, your primal and your dual bound. And that guides many algorithms we will see in this course, including the simplex method, by the way. But that we'll look into that later on briefly. But you can also use duality to obtain a estimate of how far away you are from your true optimal. So that's it. From the weak duality, you have something that it's important corollaries. So a corollary is kind of like it's kind of like the opening band for a theorem. So it's kind of like, you know, it's important, and it's kind of like a consequence of the theorem, you know, interesting consequences of the theorem. That's what a corollary is. So, and because of weak duality, basically it's kind of like you can predict relationships between primal and duals that go wrong. For example, if you have a primal that is in unbounded, remember that we're minimizing, so minus infinity is a way of saying unbounded, then it means that your dual must be infeasible. And likewise, if your dual is unbounded because you're maximizing your dual, then you can say that your primal is infeasible. You can't really tell much when your primal is infeasible or your dual is infeasible, because then it might mean that your primal or your dual are either infeasible or unbounded. So they don't really say much in that sense. But you know, these are you can improve. And this is an important thing that we're going to return to quite often in this class. But it basically tells us, you know, if it happens so that you just happen to found a feasible x and a feasible p such that this relationship holds, they actually, when you plug them in the primal objective function and when you plug them into the dual objective function, this value actually match. If that is the case, then a consequence is that x must be optimal to p and p is optimal to d. So x is optimal to the primal problem and p is optimal to the dual problem. And that's quite impressive, right? Because then it means that you just have yourself a certificate to test whether the solutions are optimal. So that means, and let's quickly prove this. To prove the first one, we use contradiction. So suppose that P is unbounded, but D has a feasible solution P. And then you can see where we're going with this, right? We just proved in weak duality that this then supposed to give a lower bound to P. But wait, P goes to minus infinity, and there's no way you can lower bound that. So you found your contradiction. So by weak duality, this is supposed to be a bound for that, but if that is minus infinity, everything breaks. So it means that there is no feasible solution for P. You can do the same thing with this just by a symmetric argument, just again using weak duality. The last one is not also hard, is not that hard to prove either. So let x be just an alternative feasible solution to P, not the one that you plug and find this. Okay, so different than x. We know from weak duality that whatever P you plug in your dual, you find a lower bound to your primal. Okay, but you just seen that for that x, when you plug it to your primal, you obtain the same value that of the objective function of your dual. So if you look at this here and you look at this here, what you just defined by accident or not is a optimality condition for the original x, because that x is less or equal than all other possible feasible x that you presume there. And there you go. You can do the same thing with the duals and you get a symmetric argument. Okay. The duals, and you get the optimality of P by a symmetric argument. But just doing the same thing, but looking at the dual, looking at an alternative P, and so on and so forth. So that's pretty cool. And the next theorem, also important, is the big star of the evening. It's strong duality. The theorem that tells you that if you find an optimal solution for P, and if you find an optimal solution, if your P has an optimal solution, so does your D, and their optimal value match. So if you find an if you can find an optimal solution for your primal problem, you can find an optimal solution for your dual problem, and their respective objective optimal values are the same. So this is the main result, or the most important result, because it gives you the guarantee that you can use your duals to go about solving your primal problems, and that's what you were looking for when you're developing this framework. So here is the proof. Basically, let's assume that P is solved to optimality. So it has an optimal solution X with an optimal basis B, and therefore we can calculate the value of B being such. We know that our reduced costs at the optimal are calculated like so. Remember that this is the part of the seed associated with the basic variables for your current basis, inverse of B times A. Now, on purpose, I'm going to say my P is defined like such. And now that might ring some bell because we calculated these P's before. And that also might come as a surprise as a consequence of this proof, because that is going to kind of telling you that somehow you can get your dual values from your basis as well, for your primal basis, which is quite remarkable. So it means that you can get your dual values from your simplex iterations for free, really, because you already have this, right? But anyway, so let's call P this term, and then it's simply just calling this B and looking again at this inequality that you get this condition, which is all dual feasibility condition, by the way. Here it is. So that is meaning that if that is P, that P is actually feasible to the dual problem. So you can, turns out that you can find your P that's such that it's satisfied. Now, moreover, we know that this is the case, replacing P again from what we just defined as. We know that this is XP, so we get this. And we know that non-basic variables are zero anyway, so what's causing the objective function value is just the original CBXP. So we just showed that this is the case. Excuse me. So the last thing is to show that there's nothing else to show, because now what we can do is to pull the corollary we just proved. Saying corollary is really hard. Corollary. Anyway, so we can, because we just proved that these things match, then we can use corollary 2.3 and get the result that tells us that, oh, okay, so that means that actually X and P are optimal to their own problems, which forms, proves what we wanted to prove with in strong duality. So we're done. So just a small remark here is it's actually a really big remark, but it's tiny in here in the slide, is that you get your dual solutions already from your simplex. They are already available whenever you're solving simplex. So that's why I was saying you can use those to kind of infer your optimality. Basically, you can try to measure how far away you are from actually satisfying this. And that can give you a good reference on how far away you are from your optimal solution. Whenever you're doing methods that can give you primal and dual, that rely on primal dual relationships. All right, that's pretty much it. All right, so this is all for this video. We'll continue in the next one talking about an interesting geometrical interpretation of what duality means in terms of the optimality of your primal problem. So see you in the next video.